So in this one, it says, Ms. Gallus and her students have decided now to perform the caffeine experiment. In their experiment, 10 student volunteers were randomly assigned to drink cola with caffeine. So they're going to drink the Coke with caffeine. And the remaining 10 students were assigned to drink the caffeine-free Coke. Were their findings statistically significant? So we're going to talk about what that means. So was there a difference? Yeah, there's a difference, but is it statistically significant? So the table shows the change in pulse rate for each student. So for each student, we took their final pulse rate, so what it was at the end after they had drank the drinks, minus their initial pulse rate, what it was when we first took their pulse before we ever gave them anything, along with the mean change for each group. So if you look at caffeine, notice you see all positive numbers. So we didn't have anybody that had a lower pulse rate after they drank caffeine. And on average, their pulse rate increased by 3.2. That would be beats per minute, right? In the no caffeine group, we had 1, 2, I think 3 that had a lower pulse rate. And so you can tell that their average change was only an increase of about 2 beats per minute. So find the difference in the mean pulse rate for the groups. So what's the difference in the mean pulse rate for the two groups? Yep. So you're gonna say that on there. So 3.2 minus 2.0 is 1.2. So you're gonna say 1.2 beats per minute. That's the difference between the two pulse rates. And then, does your initial reaction? This is just this is you. This is not. This is an opinion, kind of right now. We don't know the statistics yet. Does your initial reaction lead you to believe that they found evidence that caffeine does or does not increase your heart rate? Explain. So why do you think it does, or why do you think it does not? So you need to write a sentence explaining that. Just from the numbers that you see right here. That this is an opinion. If it's wrong, you don't get counted wrong. This is why you think that there is a difference or there isn't a difference. Okay. Now we're going to go a little bit further. So again, for some of you, you may have said, do you think 1.2 beats per minute is really that big of a difference? Is it big enough, you think, to make it for you to say that caffeine increases their heart rate, or is it too small? Is there not enough difference there? So that could be something that you talk about. What would you think? Now, what are two possible explanations for the difference in the mean pulse rate? So we did notice that there is a difference, 3.2 to 2.0. What are two possible explanations? Number one, what's the most obvious one? What could have caused that difference between these two? What could have caused your pulse to increase? What are we trying to show? Caffeine. So that's the first possible explanation, that caffeine increased their pulse rate. So that's the first possible explanation. That would mean that caffeine is doing this. That's what's happening. Caffeine caused the change. Now, what is the other possible explanation? Could be, but like they both have the same amount of sugar in them. So we've already controlled that variable because both those drinks have the same amount of sugar. So why would there be a difference between the caffeine and no caffeine? We're saying caffeine caused the change, or what else?
Caffeine or sugar, or they can.
Yeah. So basically, it may be what they did earlier. So it could just be a coincidence, is what they put, that there's a change. So it may have just happened it may have just randomly happened, right? So it said it could have just been a coincidence that the caffeine group had a bigger change. Maybe they drank something else before, or ate something before, or did something that caused a difference in their pulse rate. Okay, so it was just a coincidence. It wasn't the caffeine, basically, is the other possible explanation. That was just a coincidence that we got caffeine more. Maybe we do it another time and we get that there's no caffeine has a higher pulse rate. It just changes every time, right? So we're going to try to decide if the difference in pulse rate is big enough to be convincing. You see that word convincing is in bold. We want to know if we have convincing and if it's statistically significant. Is it a big enough difference to convince us that there is a difference between these two? So, step one, and this is what you've done already, I've given to you. Step one is going to be that you gather up 20 index cards. So, if you don't have, you guys have the index cards. If you don't, you just use a piece of paper and kind of cut those out. But you need 20 index cards to represent the 20 students in the experiment. So on each card, what I need you to do now, on each card, you're going to write one of the 20 outcomes listed in the table. Here are the 20 outcomes. 8, 3, 3, -2, 5, 4, 1, -1, 4, 5, 0, 5, 6, 1, 1, 2, 4, -1, 0, 4. Those are the 20 outcomes listed in the table. For example, you write an 8 on the first card. You write a 3 on your second card. You write a 3 on your third card, a -2 on your fourth card, and so on. Once you have written all 20, so I'm going to give you just a minute to write all 20 outcomes, and then I'll go to step 2. Move forward. So step 2, once you've written those 20 different outcomes on the index cards, you're going to shuffle the cards up. That means turn over so you can't see any of those that are written. Shuffle them up, so mix them all up, okay? Move them around, keep moving them around so that you have no order of where they're at. And then you just want to deal them out, put 10 on the left side and 10 on the right side, okay? So deal out 10 cards each. What this represents is us randomly assigning the people to the 2 treatments, okay? Assuming that the treatment doesn't affect their pulse rate. So we're just going to randomly assign it. The first pile of 10 cards that you deal out represents the caffeine group. So you're going to write the numbers for the caffeine group in your the first 10 cards. And your second 10 cards that you deal out will be the no caffeine group. And you'll write those numbers in no caffeine. So a lot of different things can happen. You could get negatives in the caffeine. You could get negatives in the no caffeine. You could get a mixture. Everybody's answer on these are going to be different. It's just the 20 numbers are randomly selected in there. So you're going to add the ones you got for caffeine up and find the average change. And then find the ones you got with no caffeine and find the average change. You need to find the mean for both groups of your index cards. And again, everybody's going to be different. And then lastly, you're going to subtract caffeine minus no caffeine. You may get a negative. You may have gotten that no caffeine has a higher one than caffeine. So we've got it. So you're going to subtract the 2 groups' averages. So you're going to go in and put their average and subtract those 2. And then we're going to see what everybody got. We're going to make a little dot plot on the board and see what you got. Yeah. So as soon as you've got the caffeine and the no caffeine, you're going to put a dot up there for your. So there are 10 dots on there. You see 1 dot all the way, yes, at -2. 1 dot is -1.4. We had 1 person get -0.8. 1 person got -0.4. 2 people got 0. 1 of us got 1. 1 got 1.1, and 2 of us got 1.2. So those are our mean differences. Caffeine minus no caffeine. This is the difference that we got. What does each dot represent on here? So this would be, so each dot represents the difference in the mean of caffeine and no caffeine in one trial, right? So for each person. So for one trial, for one group, each dot represents the difference in means. Now, this shows if caffeine, this is showing if caffeine would have no effect, right? Because we're just randomly choosing numbers to go in each group. So this is the difference in means if caffeine has no effect. So that's what each dot is showing, because we didn't pick the ones that went in caffeine and pick the ones that went in no caffeine. We randomly assigned them to the groups by just shuffling the cards. So that's what each dot represents, the difference in mean, caffeine minus no caffeine, for one trial when caffeine has no effect. So if we assume that caffeine has no effect on the other. Okay, next, number 5, what percentage of the dots are greater than or equal to the difference of 1.2 that was found in Miss Gallus's experiment? So, luckily we just barely got some. So anything 1.2 or more, we would circle. Well, there's only 2 of them. So there are 2 out of 10, which is 20%. So 20% of ours are greater than or equal to what she got in her experiment. So we're going to interpret this percentage. Okay? I'm going to explain this to you. And I'll move it over onto the board. So this 20% is right here. And I'll erase the dot plot now. 20% says, assuming caffeine has no effect on heart rate, there is a 20% probability of getting a difference of 1.2 or more purely by chance. So, because that happened just by chance. You didn't just, we just randomly wrote the numbers down and picked them, okay? So, assuming caffeine has no effect on heart rate, there's a 20% probability of getting a difference of 1.2 or more purely by chance. Experiment, what we did is we assumed that caffeine had made no difference in heart rates because we put them all into one stack, all 20 cards, and we just randomly gave some to caffeine and some to no caffeine. So we assumed there was no difference between the two groups. So if we assume that there's no effect, that there's no difference between the two groups, there's still a 20% chance, because it happened 2 out of 10 times, that we got a difference of 1.2 or more just by chance. There's a 20% probability we got that just by chance. So now we get to the conclusion, basically. Do you think the difference we found from our experiment is due to the caffeine, or has it occurred purely by chance? And this is where we're going to talk about what statistically significant means. So as we go down here, notice, if there was less than or equal to a 5% chance, then it would be very unlikely to happen on its own. So it would be due to the caffeine. So 5% is our key number. If you can just randomly do something and it has less than a 5% chance of happening, of occurring just by chance, then we could say, oh, there's something going on here. But if it's greater than 5%, and ours was 20%, then we would say that's not very unlikely, so it could just be a coincidence. So when we did these index cards, we found that 20% of those had 1.2 or more. So it's not that unlikely for there to just be a difference, just randomly. So it could just be a coincidence, which means it is not statistically significant. So you need to see the difference between statistically significant and not statistically significant. Something will be statistically significant if it has less than a 5% chance of just happening randomly. But if it has more than a 5% chance of happening just randomly, then we can't really say that the caffeine actually caused it to happen. if we want something to be statistically significant, typically we need to get a bigger sample size. So we only had a sample of 20. So bigger sample sizes, doing it more often, we can hopefully get a big enough difference. So basically, in this case, we found out that 1.2 really wasn't a big enough difference to say that the caffeine actually caused that to happen. So those are keywords that you're actually going to use, and 5% is going to be used in units 6, 7, 8, and 9 later in the AP stats. So we will be looking at that 5% rule later on. Okay, so I'm going to take you to the big ideas next. And then you have that check your understanding problem. So I'm going to take you down to the big ideas. We'll go over those really quickly and move forward. Okay, a couple of big ideas. There's a lot in here, but they're important. 3 big ideas on the left side, and then talking about statistically significant. Okay, sampling variability means, so in everybody's sample, we had sampling variability. Y'all notice that? That means it varies from sample to sample. You all had the same 20 numbers on your cards, okay? But sampling variability happened, which means different samples yield different estimates. That means if Judy goes out and takes a sample of 20 people, she'll get an answer, and then if Giselle goes out and takes a sample of 20 people, she'll get a different answer. They're doing the same thing. So that's called sampling variability. Okay, it's going to be a little bit different in each sample. Larger samples, and I told you that earlier, the larger your sample, the more accurate your result. So we only had a sample of 20 here for each of us. If we would have done 100 cards, 100 students, then maybe we would have gotten more results, right? So larger samples produce more accurate results. And then we talk about a margin of error. So a margin of error tells you how far you may be off by. So there is the estimate plus or minus the margin of error. So you want your margin of error to be really small. In polls that they're doing for the election and stuff, if the margin of error is small, that means the poll is very accurate. If the margin of error is big, that means it's not as accurate. So that's the big difference there. And then our two big things here, statistically significant means when results from a study are too unusual to have occurred purely by chance. So basically they happen less than 5% of the time. It's so unusual or so big of a difference that we know something's going on here. Okay, that makes it statistically significant. And then in a simulation like the one we did today, you want to say how many are greater than or equal to what your sample was. If it's less than or equal to 5%, that means it was statistically significant. And if it was more than 5%, that would mean it is not statistically significant. And in our sample, we got 2 out of 10, which was more than 5%. So we had to say that it was not statistically significant, that it could have happened just by chance like it did today with the index cards. This says, how much did National Football League NFL players weigh on average? In a random sample of 50 NFL players, the average weight is 244.4 pounds. So that's how much we got when we sampled 50 of them, okay? Just to give you a reference, there's probably 50 players on a team, and there's 32 teams, or 30, how many teams in the NFL? 30 to 32. So if there's 30 teams in the NFL, let's just say average, I think it's 32. But 30 teams times 50, that's going to give you a total of about 1,500 actual players in the NFL. We're sampling 50 of them. So it's a good sample, but it's not all of them, right? So do you think that 244.4 pounds is the true average of all 1,500 NFL players? Probably not. Okay, so explain your answer. So it's just a sample, right? So it's the average of that sample of 50, but could it be a little bit different from there? Yeah, of course it could, right? If we knew all 1,500, it wouldn't have to be exactly 244.4. It should be probably kind of close to there, because we have a sample of 50, but it doesn't mean that all 1,500 players, that's what their average is when we take a sample. Samples should be close to the population, but it doesn't mean it has to be exact, right? B, if another random sample of 50 NFL players was taken, would you expect an average weight of exactly 244.4? If we did it again, say if we sampled 50 more, do you think you would get an exact weight of 244.4? No, because of what? What's the word there? It's the vocabulary word. Got the vocabulary word in your big ideas. What happens when you take different samples? Yeah, sampling variability, right? So you do not expect, when you take another sample, you don't expect to get exactly 244.4. You expect to get somewhere close to that or around that, but sampling variability happens. So you may pick a couple people that are actually a little bit way more in your sample, and the next person may pick a few people that weigh less in their sample. So there's going to be some sampling variability, meaning it's going to change a little bit with each sample, depending on what 50 players are in your sample. All right. C, estimates are usually given with a margin of error. So margin of error is a big key word here. It tells us how far off it can be. The margin of error of the estimate 244.4 is 14.2. So that means 244.4 plus or minus 14.2. So if we subtract 14.2 from 244.4, what do you get? 230.2, and then if we add it, 258.6. So basically that's our margin of error. That tells me that if I got 244.4, it really might be off by that much. So really it's probably somewhere between 230.2 and 258.6 is the true average. Now, based on that interval that I gave you right there, would you be surprised if the true average was 260 pounds? Yes, it's not in our interval. 260, yeah, you actually would. 260 is not within the margin of error. So the margin of error basically tells me how far, basically you expect the true average to be somewhere in between that. So if it's outside of that, that's unexpected. That doesn't happen very often. So we would be shocked if it was outside of our margin of error. Okay. So basically, D was in your check your understanding too, which would be more likely to give an estimate close to the real. When it says the true average, it means for all weight of NFL players, a random sample of 50 players or a random sample of 100 players. 100, right? So we're thinking logically here. 100 players, and your reasoning is because why? Absolutely. And that's true. I mean, you would think about, before you even got into AP statistics, you should already been thinking that. The bigger your sample, the more accurate your results should be. So if you go out and poll 50 people and get the results, and somebody else goes out and polls 100 people and get the results, I'm going to take the person that polled 100 people if y'all are doing the same thing. So if y'all are both just randomly selecting NFL players, I'm going to pick the person who randomly selected 100 NFL players over the person who randomly selected just 50. So that's your bigger samples give more accurate results. All right, so what I've done for you is a lesson on this. So it'll be on Canvas, but the quiz is on